All right, let's take a look now at what's happening with our sound waves in terms of the trigonometric functions that we've been looking at. First of all, in orange dashed line, we've got our standard sine curve with features that you should start to become pretty familiar with. The way that we rise up to a peak here at pi over 2 radians, come back down, back to 0 at pi radians, and finally wrap up our first cycle at 2 pi radians. So this is our standard sine curve. It has an amplitude of 1, which you don't really need to write, and a frequency of 1, because we see one full cycle within 2 pi radians. Below that, I have the equation for our sound wave that we put into Audacity earlier. First of all, the amplitude has been reduced to a half, and the frequency has been increased to 240 hertz. Now, technically, hertz is the number of cycles in 1 second, so this is not quite precise, but we'll do this because it's simpler for our purposes. And when I look at this wave, I get this wall of, almost looks like a rectangular block, because what we have here is the reduced amplitude, or slightly less loud, that peaking out at 0.5 and bottoming out at negative 0.5. But within this stretch from 0 to 2 pi, instead of having one cycle, there are 240 cycles of up and down that are occurring within this shorter space. So that higher frequency gives us the tone that we heard earlier. In addition to that, I've got the second sound that we played, which also just looks like a wall of red here, but the same amplitude and the sine, but the frequency is increased to 248 cycles. So again, zooming in here a little bit, we can see that these are very similar looking waves, but they are offset a little bit by that change in frequency. And between 0 and 2 pi, we've got 240 in the blue and 248 cycles occurring within that window. But here's where things get interesting. When we combine these two graphs together, we get a unique result. Here we can see on this line in Desmos that my A3 function is going to be equal to the sum of A1 and A2. In other words, combining this and this function together. And when I reveal that on the graph, what you see is this pulsing behavior, and I get that offsetting wobbling tone that we were hearing in Audacity. And you can kind of count out what we were hearing within those seconds. The 1, 2, 3, 4, 5, 6, 7, 8 peaks of that offset. So we heard this tone that I won't try to replicate with my mouth because it would be humiliating. But what we've got are these combining waves where they amplify one another and cancel each other out. And this is the interference that's going to be a key element of our next little project. And it'll be a lot easier to visualize those with simpler graphs. But hopefully you can kind of connect the idea of the sound that we heard with these functions described mathematically, and that the adding together of these functions in this sort of simplified form gives us or demonstrates that wobbling sound wave that we're hearing as the amplitude increases and decreases over time. Let's take a look at our base function again here, and I'm going to pause this here now so I can get a better window to click on my functions. All right, that's better. So let's turn on g of x here, which would be right now exactly the same as f of x. We can see it kind of laying on top of that orange. And the value of b right now is 0, so I'm not offsetting g of x at all at the moment. But as I change b, what you'll see here is a shift in the phase, or a horizontal translation of the sine curve. This is one of the translations that we explored earlier, so hopefully you're comfortable with how that behavior looks and why it's moving that way. But an interesting thing occurs when I combine f of x and g of x. And here I can see that together, when they're working together, we're amplifying the sum of those two. And when they're both at 0, obviously the result is at 0. But as I begin to change the phase or shift the phase, I can see that the resulting wave is being altered as well. And in fact, I can manipulate this in a way to almost completely eliminate any of the resulting wave at all. So if I combine the orange curve with the red curve, at any given point on the graph, I'm combining this 0.408 with this negative 0.408. I'll get the exact spot, but you can see that adding those two together will give this sort of resulting flattened out curve. So you can effectively eliminate waves if you are able to combine a wave with its opposite, and that's going to be very important to us soon.